So I'm from South Africa. I'm at a university called the University of South Africa, which is enormous. But it's all distance education. So we have, I think they say 370,000 registered students. It's crazy, but it's actually quite a nice place to work because everything is online. So it works well for me and research. Right. So what I'm going to talk about firstly is this concept of meta-learning and performance complementarity. And then I'm going to highlight 5 case studies. Now, some of them is completed research and some of it is very much research in progress. I want to say that I think some of my students might be listening to this talk. If your work is highlighted here, I hope I do it justice. And if your work is not highlighted here, it doesn't mean that it's that it's less interesting, or it just means it might not fit into the story I wanted to tell today. So the 5 case studies are firstly the constraint handling for evolutionary algorithms. Then I want to talk about feature selection for classification, and then time series forecasting, and then approaches to regularisation in deep neural networks, and topic modeling algorithms. Those are the 5 case studies that I want to highlight today. Great. So firstly, meta-learning. So meta-learning has different meaning depending on who you're talking to. So if you're reading a machine learning type thing, there'll be lots of different definitions. People say things like learning about learning, or the process of learning across learning tasks. But I would encourage you to go back to Kate Smith-Miles's seminal paper in Computing Surveys in 2008 for a really nice introduction to this and an overview of what meta-learning means, called the Cross-Disciplinary Perspectives on Meta-Learning for Algorithm Selection. And another book that's quite useful is this book by it's Van Schuren and colleagues, but it's specifically looking at meta-learning in the context of automated machine learning, AutoML, and data mining. So it's not so much about optimization, but still it's a useful resource because it does provide a nice overview of how meta-learning is understood specifically from the machine learning community. So I like to think of meta-learning as using metadata, so that's data about algorithms and performance and so on, to develop models with the aim of using algorithms more effectively on future tasks. So this picture here is actually from the meta-learning book. And so the purpose is to develop a meta-level model. So you actually want to make something that encapsulates intelligence around how these algorithms work. So you start with generating metadata, which is you have a whole lot of problem tasks or data sets or combinations of those, and you have a whole lot of algorithms that can solve those tasks, and you evaluate the performance of the algorithms on those different learning tasks. I'm just going to move my screen so that I'm not looking away all the time. There we go, that's a bit better. And then you evaluate the performance of the algorithms on those tasks, but you also characterize the tasks and or the data sets in order to describe them in a meta way, in a higher level, more abstract way. And then then you have a metadata data set. And the metadata dataset includes information on different algorithms, different tasks, different data sets, different characteristics of these problems. And it also includes the performance data. And from that, you can develop a meta-learner. You can use some sort of a meta-learner in order to develop a model that you can then use in some sort of way in the future. But that model encapsulates the intelligence around how these algorithms work. So that's how I like to think about it, is developing models. Now, a lot of other people, when they talk about meta-learning, they think parameter tuning, transfer learning, things like that. And that is also meta-learning. That's why I struggle with the title, because it has different meanings to different people. But what I'm talking about is this thing. I'm talking about this thing, this idea of learning from performance data of lots of different tasks, and then developing a model that encapsulates that learning. Right. So it's always useful to go back to this 1976 model by Rice, which is the algorithm selection problem. So this is when you've got an algorithm. Well, firstly, you've got problems. So you've got a whole set of different problems, instances of a certain class, and you have a bunch of algorithms that you can use as alternative candidates for solving your problem. And you also have some way of measuring the performance. Now, you might have different ways of measuring the performance, but the point is that you can use trial and error to say, I've got a problem, I solve it with all the algorithms, and then I pick the algorithm that solved it the best, and then that's the one that I'm going to use. But now you've got a new algorithm, a new problem. Which algorithm are you going to use? Well, you can just use them all. But the idea with algorithm selection is to say, let's try and abstract the knowledge. Let's try and describe our problems in terms of the features that they have. So on a more abstract level, we describe our problems in terms of features, and then we can go from the whole purpose of algorithm selection is to find this mapping, to say, if we know what kind of features our problem has, we expect that this algorithm is going to be the best at solving it. So the aim is to find this mapping. So I just find this is quite a useful framework to come back to every now and again when you're working in the space. So there's lots of research to be done in all kinds of aspects here. There's research in terms of analyzing the problem. So saying, if we've got a whole lot of problem instances, are they maybe we're setting up a benchmark for testing new algorithms, a benchmark set. How do we create new ones that are representative of real world problems? There's work in terms of extracting features that are meaningful and that will hopefully help to map to algorithm space. There's work on deciding which algorithms you're going to use in your portfolio. There's work on performance metrics. So there's just a lot of work to be done here, but it's all about taking a step back and saying, do we understand all of these spaces well? And can we find better ways of doing things intelligently according to the context, right? So all of this is hinged on this notion of performance complementarity, which is a nasty, it's a horrible word to say. So performance complementarity, I think, was first coined in the paper by Pascal Kirschke and colleagues called Automated Algorithm Selection Survey and Perspectives. That's in Evolutionary Computation in 2019. I don't think it was used before this paper, but I might be wrong. Please tell me if you found it being used anywhere else, because it's hard to say, but it captures this idea where different algorithms perform well on different types of problem instances. So, and when you're in a situation where you say, which is the best algorithm to use, and your answer is, well, it depends, then we have performance complementarity, because it depends on the context and the problem and so on and so on. So it ties with this idea that there's no single best algorithm. but a portfolio of candidate algorithms, and they've got complementary strengths. So some are good in certain situations, but they're bad in other situations and so on. So it is kind of related to this no free lunch thing, except it's in a particular context. But it's this whole idea that you sometimes certain algorithms are good and sometimes they're not. And meta-learning only makes sense when there is performance complementarity. So we know that performance complementarity does seem to hold for many, many people have shown that it does hold for a large class of NP-hard decision and optimization problems. But when you're starting a new study, I think it's always important to just show that it does exist, because there's no point in analyzing which algorithm to use for a new problem if there is one algorithm that's always the best. So just do the performance complementarity test first before you go further into analyzing things. So case study 1. This is something I've been busy with for quite a long time, ever since my PhD, actually. When I did my PhD, it was looking at the landscapes of continuous optimization problems, the search landscapes, and then trying to understand the behavior of particle swarm optimization algorithms and when they fail and when they do well and so on. And after that, I started thinking, but these are, we're always using these artificial benchmark problems and so on. And in the real world, almost all of the benchmarks have constraints. And so I started thinking about how do we characterize problems that have constraints, and so I ended up in this domain. So this work on constraint handling is started with I started it on my own, and then I in collaboration with Irene Moser at Swinburne University, and then now I'm currently collaborating with Arnaud Lifuga at ULCO in France. So what we're talking about when we're dealing with constraint handling is we can think of it as, so we're minimizing or maximizing something subject to some constraints. So we can think about it as a landscape with holes in it. So you've got all these solutions and you're trying to find maybe the one that maximizes some objective or minimizes some objective, but there are a whole lot of solutions that are infeasible. So you can't use those. And so how must the search algorithm, so specifically we're looking at evolutionary algorithms, how must the evolutionary algorithm navigate the space if there are holes in the landscape? And what the first thing that we kind of thought about was that we shouldn't think of them as holes, we should think of them as other landscapes. So let's say, for example, this top figure is a two-dimensional landscape where we're trying to find the minimum, which is that purple part there. But this here is the constraint. So it tells us that there's a whole region here in the middle where the constraints are not violated. And then we have this notion of the extent of the violation. So in these parts where that part is going up and so on, there the constraints are violated, and to a larger degree. So the idea is that you can navigate the space in order to get to the feasible regions. And just, you can then take these two and, constraint handling approach, a typical constraint handling approach is what we call a penalty approach, which basically adds these two together, and then the search algorithm navigates this space. But you'll see that this will end up not finding the best solution because the one that's here is violating the constraints, and yet it will be anyway, the point is that navigating these spaces is what I was studying with this constraint handling. Okay. So the first thing we did is, that was with Irene Moser, we looked at performance complementarity. So here we were looking at constraint handling techniques used with the same evolutionary algorithm. So what was interesting about this study was that we looked at problem instances in both the combinatorial and continuous cases. So we developed a metadata about algorithms, about the same sort of base algorithm with the same constraint handling techniques in different domains, search domains. And we looked at okay, so here figure 2 shows a distribution of algorithm ranks. So we had 1, 2, 3, 4, 5, 6 constraint handling techniques used with an evolutionary algorithm. No constraint handling, death penalty, weighted penalty, feasibility ranking, epsilon feasibility ranking. Don't worry about it. It's just different approaches and a bi-objective approach to constraint handling. And we found that over this set of 142 constrained optimization problem instances, there was performance complementarity. So all of the constraint handling techniques had the worst rank of 6 and the best rank of 1 on at least one problem instance. On average, the bi-objective approach was the best. So it had the lowest rank, rank where 1 is the best. But they all were good in some instances. We also looked at this notion of failing, and so a constraint handling technique failing, and that's defined in the paper what we meant by fail. But we found that, everyone, no constraint handling and bi-objective, failed in 42% of the cases. So in other words, even though it was a good performer, it was still failing on a whole lot, just less than half of the problem instances. So this is clear performance complementarity. This is saying that every algorithm has its place, but even if one is the best overall, it's better not to use it in 42% of the cases, and there we should rather be using one of the others. And so then we took it further and we said, okay, let's now, before, this was now work with Arno, where we looked at the knapsack problem, just as another example of constrained optimization problem. And we showed that there was performance complementarity with these different problem instances. And we showed in this study, we looked at, maybe just look at this one on the left. This is the algorithm, the rank of the algorithm where 1 is good. So here we have a linear penalty, a quadratic penalty, feasibility rules, and bi-objective. So we just use the 4 different algorithmic approach to constraint handling. And this is, we've called it budget. It's actually the wrong word. It should be evaluation. So this is like how long the algorithm is, the genetic algorithm, or in this case, it was just an evolutionary algorithm, how long the evolutionary algorithm is running for. So at the beginning, they all obviously doing equally. Anyway, they start off, and then the linear penalty does really badly, and the bi-objective approach does really well in the beginning. And then after a while, the bi-objective approach does worse and the linear penalty starts doing better. And we see the quadratic penalty at the end, after 100,000 function evaluations, the quadratic penalty is doing the best. But you see that changing, and it depends on where you are. So we included how far you are in the search as one of the features of deciding which algorithm you should use. Okay, so we showed performance complementarity here. Right. And then we took it further and we said, okay, can we do this online algorithm selection? So with this knapsack problem, We did it I did it in other contexts as well, but this one is nice and easy to understand because most people understand what a knapsack problem is all about. So we took these 4 constraint handling techniques on 1,000 knapsack problem instances, and we looked at 5 landscape features plus the budget now, which is not really a budget. It's more just where how many evaluations you have to do your search. So the idea here was that there's an offline training phase where we have the information on how all of these how all of these constraint handling techniques have performed on all of these problems. These are now the training problems. And we also have information on what the landscape features are. Now, when I say landscape features here, I'm talking about things like what percentage of the search space is feasible, or how correlated is the violation, the level of constraint violation with the objective, or how contiguous are the search, are the constrained, or the unconstrained areas. So you have these islands of feasibility or islands of infeasibility. How contiguous are those? Are they split up and all over the place, or is there a large feasible region? That kind of thing. So we have numbers that quantify that, and that's based on landscape analysis. And the whole idea is you do this offline training to develop a decision tree model, and then you derive rules from these trees, which you then can use in an online switching strategies. Okay, so here's just one example for the linear penalty. So if we use these decision tree models to predict when a strategy is going to be one of the best. So instead of having in landscape, I'm going to come back to this later. Instead of having a algorithm selector that has as the leaf nodes the algorithms. So quite often when you look at algorithm selection solutions, they will have the features in the tree, and then at the bottom you have the decision of which algorithm must I use. Instead, what we realized works better is to have one tree per algorithm, and the tree then decides when it will be one of the best or not. So what's useful about that approach is that different features can be important for different algorithms, but I'll come back to that. So in this case, we've got the ratio of feasible boundary crossings. That's how contiguous are the feasible areas. If that number is less than 0.005, then it is outperformed. So it's not a good strategy. But if it's greater than that number and you have 1,000, you have greater than 1,000 function evaluations available, then and the feasibility rate is less than a certain amount, and so on, then it's predicted to be one of the best. Okay, so the idea is here that you can take this tree and you can make a little if statement in your code, and then as the evolutionary algorithm is busy searching the search space, it is collecting information on the landscape, on the features. In other words, it knows how much it's already searched, and it can pick up how many of the solutions it's seen are feasible. So it has an estimate for the feasibility rate. It has an estimate for how contiguous the search spaces are, because as the evolutionary algorithm progresses, it goes from feasible to infeasible to feasible to infeasible, or they're all feasible or they're all infeasible. And that tells it, then it can keep track of the features of the landscape, and it can make its decision as it goes along. So I hope that I've got this, yes. So we then test the performance of this, what we call a landscape-aware constraint handling technique on a different set of problem instances. So this is a testing sample. So we look at linear penalty, quadratic penalty, feasibility rules, bi-objective. We look at a random switching strategy just as a sanity check, something that just randomly chooses a different algorithm, a different constraint handling technique at certain intervals, and then our landscape-aware switching. So this one on the left is the algorithm rank. So that's how the lower is better. So our landscape-aware approach is generally low down, which is good. So it's doing right at the end. You see that quadratic penalty actually does better, peaks it. But what's interesting is that landscape-aware switching is good all along, and then it's never the worst. This is the one of the worst. So it's never one of the worst strategies, whereas all of the others have a chance to be one of the worst at different stages. Okay, so it really works well, this idea of capturing the intelligence of when each constraint handling technique is appropriate. Okay, case study 2. So this is actually one that Kate knows well because she examined Werner's PhD. She was one of the examiners. So this is the binary problem of you've got to do, you're doing machine learning. So you're doing classification and you want to decide with a kind of numeric or categorical, the table data set, and you want to decide which features are important and which are not. So you do feature selection. Now, there are many different algorithms for doing feature selection. And the question is, what's the most appropriate feature selection algorithm to use in different contexts? So I was co-supervising Werner, Andres, he's now at Stellenbosch University. He was the main supervisor. And in the process, we also collaborated with Gabriella in Stirling in Scotland. So the first thing we did is we used landscape analysis to try and get a sense of what's the nature of the search space. And we made this, we came to the observation that there were these large plateaus. So what you see in the top is is the breast. So that's whether whether you predicted to have breast cancer or not. This is some vowel classification problem. I'm not sure. Oh, anyway, this is some zoo classification problem. It doesn't matter. But these are 3 different data sets. And these are what we call a local optima network, which is a abstraction of the search space. And every dot in the graph, every sphere in the graph actually, is a local optima. And the red ones are the global optima. So what we discovered in the analysis of these problems is that actually these global optima form plateaus. So you can, all the best solutions sit next to each other. You can get from one global solution to another global solution by just flipping one bit. So it means that these form what we call a global plateau, this is just a different kind of local optima network that shows the plateaus as rectangles. So we see this phenomenon in the feature selection problem, and this is these large plateaus. So we have, for example, on the Zulon, we see that there's the global optimum, the best solutions is a small plateau, and there are all these other large plateaus. So what that means is that when you flip a bit, in other words, you decide, I'm going to include this feature in the machine learning task or not. You flip a bit, it has no effect on the performance of the classifier. And that's what neutrality does, is it's a phenomenon of the search landscape that says that if you change your solution slightly, it has no effect. So that makes it hard for search, because if you're searching this space to try and figure out what's the best combination of features to include, and you're trying out different ones, and nothing happens if you switch one in and out. The other phenomenon that's important is that all the global optima are connected. So in other words, all of the good solutions are sitting together. So that was the first thing we did, and then we did the performance complementarity. So this was now looking at different feature selection algorithms. So we've got AMSO. I can't remember what this was. This was some sort of swarm-based algorithm. That was a GA feature selection. SB, I think, was sequential backward feature selection, sequential forward feature selection. These two were filter-based methods. So it was a principal component, information gain, feature selection. So these our filter-based methods work quite differently. They just look at the data set and they measure correlation and things like that, and then use that to decide which features are important. Whereas these are wrap-up techniques, which actually use the performance of the classifier to decide which features to use. So what we did here is we just looked at, does it make a difference? Is there performance complementarity? And we saw that, yes, there is. So if you just look at the best column, AMSO was the best in 13% of the cases, the GA in 29%, and so on. And these were also good on some of the instances. They were the best on some of the instances. So we have the situation where some are the best, and they also all were the worst on some. So, for example, AMSO is a kind of average performer because it's hardly ever the best, but it's also hardly ever the worst. Okay, so we showed performance complementarity. And then we did an instance-based analysis. So this is now a fantastic tool called Matilda, which you probably all know about because it's developed in Melbourne by you guys. But in this case, we were looking at 7 feature selection algorithms, some of them filter-based, some of them wrapper. And we took 306 classification data sets. They had a range of features, so from anything from 2 classes to 186 classes. We looked at 22 meta features. So now what was interesting about this study is we had the features of the data set. So it's a classification problem. So things like how many classes are there is a meta feature. How many instances do you have for the training? So those are the data set features. Then we've got information science features like the correlations, the information gain, those things, the skewness, those kinds of measurements of various of the information inside the data set. But then we also looked at some fitness landscape metrics. And there in particular, we were interested in things like neutrality, because we'd realized with a first study that sometimes you're going to have these big plateaus. So we looked at we looked at metrics for characterizing neutrality and some other aspects of the landscape. And we used a performance metric called baseline fitness improvement, which Werner, who was the PhD student, he had to propose a new performance metric because none of the performance metrics were suitable for meta-learning. So in this case, you can imagine feature selection. If you use, let's say, accuracy of the classifier as your performance metric, you're not really measuring the feature selection aspect of it, because what happens if it's an unclassifiable problem, you know? So the idea is to say, if you do no feature selection, what is that accuracy or the performance of the classifier at that accuracy? And then what is that? Does it get better or worse if you do feature selection from that baseline? So that was the idea of that performance metric. So if any of you have used Matilda, you'll know that there's a very involved and clever process of dimension reduction. So the idea is you give it a metadata base, which includes the features of your problem instances and your, oh goodness, I'm I'm going to have to speed up here. Okay, so it does this dimension reduction using the performance of the algorithms and the features of the problem instances. And what's interesting here is which ones come out as the most significant. And these can be seen as the most important features for meta-learning. So in our case, it was the size of the largest neutral plateau. It was a neutral metric number 2. Okay, so that's basically if you have big plateaus or not, was an indicator of that distinguished well between the performance of the algorithms. Then there were 2 landscape metrics. The information gain in terms of the skewness of the information gain with respect to the class, that was another one. The number of features and the number of instances. So those are also meta features that featured. And then what's great is you can do things like this. So here on the left, we have number of features, which is one of the meta features. So if you've got a data, remember we've got these classification data sets. Sometimes it's binary classification. So there are only 2 classes. Sometimes there are 186 classes. So this, how many classes there are, is this color. So you see yellow means that we've got lots of features, oh, sorry, this is features, not classes. This is number of features, which means this is not meta features, this is features. These are the attributes in the classification data set. So how many attributes have you got for helping you to do the classification? So when you've got lots of features, it's yellow. And so we see these 2 bands. On the right here, we have the same instances. So every dot is a data set that we're doing classification on. The GA on the right here, we see that's good performance, and the orange is bad performance. So you very clearly see that the bad performance of the GA is linked to the number of features. So if you have lots of features, the GA doesn't do well. And that makes perfect sense, because if you have lots of features, then you've got a huge search space, a binary search, because for every feature, you've got a 1 and a 0. So it increases the dimension of the search space significantly for a GA. Here's another example. This one is the number of instances. In other words, how much data have you got for training? And this on the bottom here, we see there are lots of instances on the bottom right. This is the information gain feature selection. And it performs well when you've got lots of instances. It performs poorly when you don't have a lot of instances. So if there's not a lot of information to work out what the information gain is, and then it doesn't perform well. Okay, so this is a fantastic tool for doing this kind of analysis. And then included in Matilda is this support vector machine, which then it basically delivers to you a meta learner that can predict choose an algorithm depending on the features of the data set. So we see here, these are our candidate algorithms, 1, 2, 3, 4, 5, 6, 7 of them, 7 candidate algorithms. This is their average performance. And then we've got the oracle, which is the kind of, if you always choose the best algorithm. And then we've got the algorithm selector, which has a better performance a baseline fitness improvement, higher is better. So it was second, it was the best on average compared to the others. Right, so we have an algorithm selector that is intelligent based on the meta features. Right, let's keep going. Okay, that means, never mind that. This one is an interesting case study. So this is time series, univariate time series forecasting. What makes this so interesting is that it's done. There's a lot of people who've done studies on meta-learning within the space. So this is with a PhD student, Evans Reba. He's a current student, so this is work in progress. And my co-supervisor is Edna Mudima in my department. So if you think about time series, it makes sense that they're features that describe it. I mean, if you look at this series compared to this series, compared to this one, compared to that one, they definitely have different characteristics. And this idea that you can extract features from these to describe what makes this series different from this series, for example. There's lots of it. So there's seasonal period, there's seasonality, trend strength, spectral entropy, and there are whole packages in R and other languages that are available for extracting meta features from time series. So the idea here is to say, okay, we've got all our features, we can extract them, we've got our data sets down here, and then we've got the target, which is what is the best method to use? Should we use ANN, TBATS, and then the meta learner must now figure out which is the best method to use. Okay, but the point is that people have done this. So there's this Talagala et al. In 2018 developed this thing called F-forms, which was exactly this offline training. You have your training data, which is your part of your series that you're training on, and then you've got your test data, which is the part that you're testing on, so on, and you extract your features, you train a classification algorithm, and they used a random forest classifier. And then you've got a brand new time series. You calculate the features, you use the random forest to tell you which method to use. So the which method to use is the target of this random forest classifier. Okay, so they've done it. The point is that this was limited to statistical forecasting methods. And the random forest classifier had 15 classes. So this target here was 15 different statistical methods, from ARIMA to TBATS to whatever, exponential smoothing to, all of these statistical methods. So we thought, okay, the point is that this has been done, but it didn't work that well. So it wasn't competitive on the competitions. So we wanted to try and find out why. So can we improve on this to make it competitive? You know, because they have these competitions, they call them the M competitions. I think they've come to M4 now. But it's these massive competitions where they have thousands of data sets, some yearly, some monthly, some weekly, some hourly, and so on. And then there's the winner of the competition for that round, and so on. And the winners are always lately ensembles. And this, if you look at the performance of techniques like this F-forms on these competitions, they don't do that well. So great idea, very intelligent, but not really worth it. So we wanted to look at why, can we make it better? So the first thing we did was to show that machine learning methods actually should be included here. So we have this paper that we wrote, machine learning, well, Evans wrote, machine learning methods do have a place in univariate time series forecasting, because in this time series forecasting community, the statisticians generally do win. They kind of dominate, and they don't think there's much space for machine learning. So what we showed in this paper was just that there is performance complementarity. Sometimes a belief neural network or support vector regression would work the best. Sometimes. So there was always sometimes they're the best, but compared to the statistical techniques. Great. So then we wanted to see, can F forms be improved? So the first thing we did was to change from that multi-class to binary classification. So that idea that instead of trying to predict 1 out of 15 classes, so you're doing a 15 class classification problem, you make it into a binary classifier per technique. So you have one meta learner for ARIMA, one meta learner for TBATS, and so on. So it makes the classification problem easier. There are a few reasons why it's better. Is because it's an easier thing to learn, and also because certain features might be important for certain algorithms and not for others. So we found that this is now vertical axis is error. So we want to be lower. So on the yearly data, it didn't make a difference. But on quarterly data, monthly data, weekly data, the binary classification formulation of the problem of the meta learner outperformed. So overall, it was better. So it got a lower mean squared error, a lower, yeah. Right. So it works better to do it this way. Then we decided, okay, let's add the machine learning methods, because this was just the statistical methods, the 15 or so. Then we decided to add machine learning methods to it because we've shown that there's performance complementarity. Machine learning methods do well. They complement the statistical methods, and the performance decreased. So here we were adding new algorithms to the pool of algorithms that perform well, that complement, and it performs worse. So what we then looked at is this sensitivity to the number of methods, and we realized a very interesting thing. Now it's quite hard to explain this, but if you increase the number of methods that you're using in your meta learner, okay, so how do you decide which methods you're going to use? Okay, so you start off with your training, you've got your training data. On the training data, you rank them on average. So then you decide which ones are the best on average. So if you start with only 2 algorithms, the 2 that are the best on average, and you develop a meta learner with just those 2, then that was this is now the yearly data, okay, data sets. They always divide them up. So at that point, we have a mean squared error if we're using 2 with a meta learner. Then we try the same thing, but with 3, the 3 best on average, develop a train a meta learner. There's a magic number 5. At number 5, it gets to the best error. You add one more method, the 6th. You add the 6th best performer, and suddenly the performance degrades. We found it it goes down and then doesn't get much better after 5, a little bit. Sorry, the 2 lines are the binary classification or the original F forms. This is weekly and so on. So for all of them, it gets better in many of the cases. So we think, now this is something develop the metadata using many methods, but then you pick a subset and you develop the meta-learner using only a subset, because and this is something that I think we need to still try to see whether it does make it better. Okay. I must keep going. Second last. This is regularization with a master's student, Christian Oppermann, in a collaboration with Anas Bosman at the University of Pretoria. We're looking at the lots of different ways to do regularization of neural networks. So that idea in deep neural networks, you can use things like pruning or dropout, or change the loss function, or use a regularization term in the loss function, or do data augmentation, things like SMOTE. They are all supposed to improve generalization. And what Christian's done is he's shown that it depends on the data set. So we have performance complementarity here. So this is just the first step to say that something like batch normalize, oh wait, let's look at dropout is a good example, because everybody knows about dropout. So dropout, we've got 5 image data sets and 5 numeric data sets. Dropout was worse than the baseline. That means that you don't do any dropout. When you do dropout, it gets worse. But on the numeric data sets, when you use dropout, it got better, but only for 2 of the data sets. So we have this, like for balls data set, the baseline is doing no regularization. If you do things like batch normalization and layer normalization, it improves the generalization. It improves the F1 score significantly. But if you do weight perturbation, it decreases, it makes it worse. So we have performance complementarity in regularization of deep neural networks. Last one, this is with my PhD student, Darren Roos, with my co-supervisor, George Davey, also in my department. Topic modeling is where you've got a collection of documents and you're trying to cluster topics, create topics. And what he's shown is that there is performance complementarity. So we have 11 topic modeling algorithms, from things like latent directly allocation to BERT topic and so on. Got lots of problem instances. We have 10 data sets with 5 numbers of topics. In other words, like, because you have to say up front, I want 10 topics or I want 100 topics. And then we show that, well, he's shown that if we're using this as a performance metric, the normalized point-wise mutual information, then the best performers are Gaussian mixture model or non-negative matrix factorization. Okay, so this is out of 55 problems. This one was the best it was the best one in 45 of them. Yes, I think, yes. On this data set, this one was the best. Oh, no, I'm not going. Oh, this is comparing wins and losses. So it's saying that GMM was better than 45 of the data sets than combined TM as another algorithm. Okay. But the point is, it depends on how you measure the performance, because if you use another performance metric, other ones do better. And so there's a lot of performance complementarity there. So in conclusion, I like to think of meta-learning as model development, which captures the intelligence about the algorithms that we're using in computational intelligence in a model form. To use meta-learning, you must have performance complementarity, so always check for that. Traditional and simple algorithms are often effective, and we mustn't forget to include them in our algorithm portfolios. And more studies should focus on understanding the existing algorithms and the developing meta-learners for different problem tasks. So any questions? Sorry, I spoke a bit too long. Okay.